So this is what we call a static condition Newton's question. Okay? Static means what? Yeah, not moving, not changing. Okay? So in this type of problem, nothing's moving. Anytime nothing's moving, what's the net force? Right. That's something you have to keep in mind. The vector sum of all the forces acting on the sign is 0. Right? So all the vertical forces add up to 0, all the horizontal forces add up to 0. Okay? Otherwise, the sign would be accelerating in some direction or another. So we've got this wall here, and we've got a cable coming down from it that is angled 55 degrees below the horizontal. Okay? It's attached to this 35 kilogram sign. Right? So that's cable 1. Cable 2 is horizontal. It attaches to this building over here. Okay? That's our situation. Using only that information, you can calculate the tension in cable 2. Okay? Now, here's the tip I will give you. Cable 2 is pulling straight horizontally. Okay? Exactly horizontally to the right. That is all cable 2 is doing. Right? You need to figure out how hard it's pulling to the right. So you may need to identify one other force that is present here that I have not drawn. Yep. Okay. And then figure out how these cables and gravity interact to produce a net force of 0. You're going to have to do a little bit of vector stuff to do that. Okay. So we have to look at this from a vector perspective. Okay? We have a force that is pulling down, straight down. Okay? The force of gravity. And we can calculate how big that force of gravity is by multiplying 35 times 9.81, which is going to be 343.35, right?
Yeah.
Newtons. Okay, so there's a downward force. My other forces are the tension in cable 2, that's what the question wants me to solve for, and the tension in cable 1. I don't know either one of those, but cable 1 is angled.
Wait, can I guess how to do it?
Okay?
Okay, do you have to go and make sure, so like, since the sign's not moving, if you had a cable going directly this way, it would have to equal cable 2, so you would put the 343.35 going straight up and draw a triangle, and then do cos 55 times that number.
Yep. Okay, here's what we're doing. Cable 1 is pulling, cable 1's pulling at an angle.
It's
Which,
just like they have to equal.
right.
So.
It's got two vector components, right? Because it's pulling at an angle, it's pulling horizontally this way and vertically up. Okay? Since the sign isn't moving, this component of cable 1 is 343.35 newtons. It has to be, or the sign would be moving vertically. All right? See, this is what I mean. This is not mathematically difficult. It's conceptually or contextually difficult. Okay? You'd be able to see these forces that are really not there. Okay? They're in the cable, but okay, we're looking at a cable that's angled, that's pulling up and over. Well, I can figure out now how much is pulling over because I know this angle and I know this side. I'm not going to use cos though because I don't have the hypotenuse.
Okay.
I'm going to use tan because I'm looking for the adjacent side and using the opposite side. All right? So I'm going to say that the tan of 55 equals 343.35 over, we'll say cable 2 essentially. Okay, I'm looking for the tension in cable 2. Right? So if I want to solve for this, I'm going to manipulate and have cable 2 over on the other side. So I'm going to go 343 divided by the tan of 55, okay? And that'll get me the tension in cable 2. You want to kind of follow my logic there? Okay? So like I said, there's like, that's the most difficult calculation. You only do 2 calculations in this question. You figure out the force of gravity, and then you stick it in a trig calculation. Okay? But a question like this is really tough to visualize, okay? Like many Newton's second law questions are. So we'll have 343.35 divided by the tan of 55. All right, so cable 2 is pulling with 240 newtons to the right. Actually, it'll be 2.4 times 10 to the 2. Everybody all right with that one? Okay. So they become a little bit trickier when it's not all about all these forces we can see acting on it. Or now we start bringing in vectored forces. Okay? Bringing in vectored forces can make something a bit more complex as well.
We're going to get questions like that a lot.
Yeah. Okay, try this one. We're working on ones like this. This is our lab. Okay, this question here is our lab. So, there's a force of friction on the table between the 4 kilogram mass and the table. Okay, so there's a force of friction acting on the 4 kilogram mass of 32 newtons. Okay, we want to calculate the acceleration of the 5 kilogram mass. So first we got to identify the forces that are acting in the system. There's only 2. Okay, there's the force of friction. Okay, it's resisting the movement of the 4 kilogram mass. Okay, and then we've got the force of gravity acting on the 5 kilogram mass, which will be 49.05 newtons. 5 times 9.81. All right, since this is a system, what do I have to do when I calculate the net force? Right, I got to put the masses together. This whole system has to accelerate. Okay, so I can calculate the F net by doing vector sum of all forces on the system. 9 kilograms worth of mass being pulled this way by 49.05 newtons and this way by 32 newtons. Okay, meaning I've got 17.05 newtons worth of net force acting here. Okay, now the question wants to know the acceleration of the 5 kilogram mass. So if I want to calculate acceleration, I go F net divided by m. 17.05 divided by what? 9. Okay, not just the 5 kilogram mass that's being accelerated, it's the whole system. Okay, the only thing that's going to be unique to the 5 kilogram mass is direction. Okay, so when I go 17.05 divided by 9, okay, I'm going to get 1.9, actually I only have one significant figure here, so 2 meters per second squared down. Would be my final answer. Okay, because it asked about the 5 kilogram mass, I can put a direction on that. Questions on that one? Okay, here's good with that one. Okay, I want to see how much you remember from the blocks the other day. Okay, so the total friction on the system is 120 newtons. The friction acting on the 40 kilogram mass is 48 newtons. Okay, so 48 of that 120 is on the 40 kilogram mass. Whatever's left is on the other one. Okay, calculate the acceleration of the 40 kilogram block and the tension in cable B. Spoiler alert, you might have to calculate the tension in B before you get the acceleration for the 40 kilogram block. All right, and this is the thing that I missed, so, okay, when I first started looking at it. the total friction on the entire system is 120 newtons. Yes? The amount of force pulling forward is, right, can I calculate the net force on the whole system? Okay, that's what I gotta do first, okay? And it's easy to miss that, okay? So I've got my 100 kilograms of system mass, okay? And I've got 150 and 120, right? So that means my net force is 30 newtons forwards, okay? So the acceleration of the system and any part of it is going to be 30 over 100, or 0.3 meters per second squared forward. All right, so I just calculated the acceleration of the 40 kilogram mass, okay? Now that I know that, I should be able to break it down and calculate the tension in cable B. So I'll give you a few more minutes if you were stuck on getting that, because you need that in order to get the tension in cable B. Okay, let's have a look at how we calculate the tension in cable B. We can use either box at this point. Okay, I'm going to use the 40 kilogram box just because I have more information about it. Okay, so I've got 150 newtons acting forwards on the 40 kilogram box. Okay, I've got 48 newtons worth of friction, and I have the rope. Okay, so B, cable B. Okay, that's what I'm looking for. I know the acceleration of the 40 kilogram box, so I can calculate the net force acting on the 40 kilogram box by going mass times acceleration. So 40 times 0.3 will give me the net force. Okay, so that's kind of the first thing I've got to do. 40 times 0.3. All right, so we're looking at 12 newtons. 12 newtons forwards, okay, is my net force on the 40 kilogram box. That equals, okay, 48, negative 48 newtons, okay, plus B, plus 150 newtons, right? That's the vector sum of all forces. Okay, so now all I have to do is isolate B. So I'm going to go 12 minus 150 minus negative 48. That'll give me the tension in B, okay, which ends up being negative 90 newtons, or 90 newtons backwards. Okay, because from the 40 kilogram box's point of view, it's backwards.
Should we calculate it from a 60 kilogram? Do we put forward?
Then you put forwards. Technically, tension is a force that's acting in both directions, and you wouldn't actually have to put a direction on it. If it said from the 40 kilogram box's
Yeah.
point of view, then you would have to say that. But if it just asked tension, you could write 90 newtons and be done.
Yeah.
Because that's how tight the rope would be. All right, questions on how that one worked? Okay, so we're starting to kind of see now how much we have to read into and visualize each one of our problems here. Okay, again, we haven't run into anything mathematically challenging. Okay, addition and subtraction, multiplication and division is the extent of the mathematical operations. The occasional trade calculation if we have a vector involved, right? But other than that, not much. Okay, so here's one like the first one we did. This is another static condition example. So I've got a 120 kilogram mass. This is, I don't know if you've ever been to McMahon Stadium, right? They got the big speaker that hangs on the cables from the towers there. Okay, that's this thing. So 120 kilograms, okay, but I've only got two cables. They are separated by 100 degrees, right? So there's 100 degrees between these cables. Speaker's not moving. Find the tension in these cables. Spoiler alert, it's the same for both. Okay? A and B have the same amount of tension. What's the most important thing we need to know about this? That F net is 0. Right? Okay? This thing is not moving, therefore, all the forces are balanced. Okay? Now, I'm not really concerned about the horizontal components of B and A because they cancel each other out. Okay? And I can't get any numbers for them anyway. But what I am going to do is I'm going to make a triangle for each one of those cables. Okay? I know that this force here is the force of gravity. Right? It's 120 times 9.81, so we're looking at what, 1198?
1177.
1177.2.
2.
Okay, 1177.2 newtons. Okay, how much of that force of gravity does each one of those cables hold? Equal, so how much of it? No, each cable.
Oh, each cable.
Half. That's the thing you gotta get. Because a lot of people will go, all right, this side is 1177.2, except that means this thing is flying up into the air because the net force is 1177.2 newtons upwards. If you're saying each cable is holding that much, each cable is holding half of that. Okay, does everyone follow me there? So when I drew this triangle, what I really should have drawn was a red triangle and a black triangle, and made each one of them have a vertical component that was half of this number. Right? So I got 1177.2 divided by 2. Okay, so I got 588.6 is my tension, or my vertical component, sorry, of my tension, 588.6. All right, now that I know that, what's this angle? 50. Okay, that's the other thing I got to split in half. Now that I know that, I can find the hypotenuse of this triangle because I know the angle and the adjacent side. Okay, so the cos of 50 degrees is going to equal the adjacent side, 588.6, over the tension in A. So if I want to find the tension in A, it's going to be 588.6 divided by the cos of 50. Right, so each one of those cables has 9.2 times 10 to the 2 newtons. Actually, no, we got 3 significant figures. So 915, 916. Okay, 916 newtons. Okay, directed 50 degrees left of vertical or right of vertical, depending on which cable you're talking about. Okay, 55 degrees, or 50 degrees, sorry, from vertical. Right? Everybody okay with that? Okay, so we had to do a little bit of vector stuff in that. Okay? Again, it is the vector sum of all forces is 0, right? Okay. We have one more good one here. All right, we haven't talked about inclined planes yet, so let's just quickly introduce inclined planes to finish things off, and then we'll pick it up there on Monday morning. So, if I set something on a ramp, generally what is it going to do? Slide down. Why? Okay, and we always say because of gravity, which is partly true. Which way is gravity pulling this box?
Straight down.
Straight down, but it can't go that way. Why not? Normal force. Right, here's the thing. We've been told up till this point that normal force directly opposes gravity because we've only ever had it on a flat surface. Now this surface is inclined. Normal force always acts perpendicular to the surface. Okay? So on this particular mass, I've got a normal force acting this way. And now it's not equal to gravity because gravity is trying to pull this box this way. Okay? Now, these are 2 vectored quantities, right? 2 forces. The net force between these 2 forces is what causes the box to move down the ramp because they don't cancel each other. There's going to be a small component of force left that is directed straight down the ramp. Okay? Now, how do I do that? Well, I do that by adding vectors the way I've been taught to, by putting them tail to head. Right? So now I put these 2 vectors tail to head, and lo and behold, my resultant is parallel to the ramp, which just so happens to be the way the box is going to go. Shocking. Okay? This is why things work the way they do. Okay? This is the vector sum of all the forces in this question, right here. We call this force F parallel. Okay? It's 2 parallel lines beside the F. Okay? F parallel. Okay? Because it's the force, it's the sum of those 2 forces, and it acts parallel to the plane. Okay? It's what's going to accelerate that box down the ramp. It's also why we use ramps. okay? The ramp is an incline plane. It's one of the simplest machines. And an incline plane makes work easier. Okay? Why does it make work easier? If I want to take a box from here to here, there are two ways to do that. Lift it directly to that spot. How much force do I have to exert in order to do that? Yep. Well, or equal to gravity, right? If I go equal to gravity, I can move it at a constant velocity to the top of the ramp, right? Just by lifting it. As long as the net force is 0, right, I can move it at a constant velocity or not move at all. Okay? So I'd have to exert a force at least equal to the force of gravity. That's 98.1 newtons. Okay? It's big. If this is a 30-degree angle, so is this. Okay? They're similar triangles because they're involving all these lines that come from each other. Okay? That means that since this is 98.1, this is the opposite side, this is 49.05. If I want to push this thing up the ramp at a constant velocity, how much force do I have to use? Right? 49.05 newtons. Half as much as I would have to use to lift it. That's the whole purpose of the inclined plane. To make work easier. It doesn't make less work though. Okay? There is not less work to move it up the ramp. Because remember, and we'll get to this later in the unit, work is equal to force times distance. If I lift the box from here to here, this is a smaller distance than along the ramp. Agreed? So smaller force, or sorry, bigger force over a greater distance, or bigger force over smaller distance, or smaller force over greater distance. I end up doing the same amount of work whether I push it up the ramp or lift it there, but it's easier to do. I might not be strong enough to lift the box directly to the top of the ramp, but I'm probably strong enough to push it up the ramp. Okay. Everybody all right with that idea? Okay, so that's what we'll set to work on Monday. Talk more about inclined planes. Okay. Maybe just draw this diagram out though before we end for the day, okay, and just label this here. This side's the force of gravity. This side is the normal force. Okay. And then I will come around and spray your desks with the old cleaner, not the new stuff.